Right now, far beyond the planets, far beyond the last place sunlight feels warm, there is something surrounding our solar system. You can't see it. No telescope has ever photographed it. No spacecraft has reached it. But it's there, a vast shell of frozen worlds, wrapping around everything the sun controls. This is the Oort Cloud. It begins tens of billions of kilometers away, and it stretches outward for almost a light year in every direction. That's nearly 1/4 of the distance to the nearest star. When the light from the sun reaches the outer edge of this region, it's already weak, thin, barely alive. Temperatures fall close to absolute zero, minus 270 degrees Celsius, almost as cold as space itself. And inside this darkness, trillions of icy objects drift silently, leftovers from the birth of the solar system. 4.5 billion years ago, when the sun was forming, when planets were still assembling, when Earth was molten and lifeless, these objects were thrown outward by gravity. Jupiter, Saturn, Uranus, Neptune. Their massive gravitational fields scattered debris in every direction. Some pieces fell inward, some became asteroids, some formed moons, but others were flung outward, far beyond Pluto, far beyond the Kuiper Belt, far beyond anything humans have ever visited. They never left the sun's gravity completely. Instead, they settled into a distant orbit, a spherical cloud, not a ring, not a disk, a shell, surrounding the solar system from all sides. If you could see it with your eyes, it would surround the sky, above you, below you, in every direction. But you can't see it, because it doesn't glow, it doesn't shine, it reflects almost no light. It's invisible, and yet, sometimes, it sends us messages. When one of these frozen objects is disturbed by a passing star, by galactic tides, by gravitational nudges from deep space, it begins to fall inward, slowly, for thousands of years, for millions of years. It travels from the outer darkness toward the sun, and when it finally arrives, it becomes something we recognize, a comet, bright, glowing, trailing a long tail across the night sky. What looks beautiful from Earth is actually ancient debris from the farthest edge of our solar system. A visitor from the Oort Cloud. Every long-period comet you've ever seen started its journey here, in the cold, in the dark, at the edge of the sun's influence. Tonight, we're going to travel outward, past the planets, past Pluto, past the Kuiper Belt, into the most distant region that still belongs to our star. The hidden shell around our solar system, the Oort Cloud. Let's begin. When we talk about the solar system, we usually stop at the planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Sometimes we go a little farther, to Pluto, to the Kuiper Belt, and then the story usually ends. But the sun's influence does not stop there. Far beyond the orbit of Neptune, beyond the frozen debris of the Kuiper Belt, the solar system continues, quietly, invisibly, almost forgotten. This is where the Oort Cloud begins, not as a sharp boundary, not as a wall, but as a gradual transition into deep space. At this distance, the sun looks different. Its light is faint, its warmth is gone, its gravitational grip is weak, but still present. The Oort Cloud does not form a ring like Saturn's rings. It does not lie flat like the planetary disk. It surrounds the solar system in all directions, above the plane of the planets, below it, behind it, Ahead of it, a giant spherical shell of frozen debris. If the planets are grains of sand near the center, the Oort Cloud is the outer fog that stretches almost to the edge of interstellar space. Scientists estimate that it begins around 2,000 astronomical units from the Sun. 1 astronomical unit is the distance between Earth and the Sun, 2,000 of those distances, and it may extend outward to more than 100,000 astronomical units. That is nearly 1 light year. To put this into perspective, the nearest star system, Alpha Centauri, is about 4 light years away. This means the outer edge of the Oort Cloud reaches almost 1/4 of the distance to another star. Our solar system is far larger than most people imagine. Inside this vast region, trillions of objects drift silently. Small icy worlds, frozen rocks, ancient debris. Some are only a few kilometers wide. Others may be hundreds of kilometers across. They are made of water ice, methane, ammonia, carbon compounds, and primordial dust. These are not new objects. They are relics, time capsules from the moment the Sun was born. 4.5 billion years ago, the solar system was chaos. The Sun was forming at the center of a spinning disk of gas and dust. Planets were assembling. Collisions were constant. Gravity was violent. Young Jupiter, still growing, became a gravitational wrecking ball. As it moved through the early solar system, it scattered material outward. So did Saturn. So did Uranus. So did Neptune. Anything that wandered too close to these giant planets was flung away. Some objects were ejected completely, lost to interstellar space forever. But many did not escape. They slowed down at extreme distances. They settled into distant orbits. They formed a cloud, not dense, not compact, but enormous in volume. Over millions of years, passing stars and galactic tides reshaped this cloud. They pulled on it gently, stretching it, smoothing it, turning it into a roughly spherical shell. Unlike the flat disk of planets, the Oort Cloud is 3-dimensional. It surrounds the Sun like a halo, and yet no spacecraft has ever reached it. Voyager 1 and Voyager 2, the farthest human-made objects in history, are still traveling through the inner boundary regions. Even they will take tens of thousands of years to cross the full cloud. For humans, this region is effectively unreachable. It exists beyond practical exploration, beyond direct observation, which raises an important question. How do we know it exists at all? The answer comes from comets, specifically long-period comets. These comets appear suddenly. They come from random directions in the sky, not from the flat plane of the planets, not from the Kuiper Belt. They arrive on highly elongated orbits. Some take millions of years to complete a single loop around the Sun. Their trajectories point to a distant, spherical source, a reservoir of icy bodies far beyond the planets. This pattern is too consistent to be coincidence. It suggests a massive outer cloud feeding these visitors inward. When one of these distant objects is disturbed, it begins a slow fall toward the Sun. The disturbance can come from many sources: a passing star brushing the edge of the cloud, the gravitational pull of the Milky Way itself, tiny shifts caused by galactic tides. These forces are weak, but over long time scales, they are enough. An object that has remained stable for billions of years can suddenly change its path. Its orbit stretches inward. It begins a long journey toward the inner solar system. At first, nothing seems to happen. The object is still frozen, still dark, still invisible. But as it approaches the sun, something changes. Heat increases, ice begins to sublimate, gas and dust escape into space, a glowing coma forms, a tail appears, and suddenly the object becomes visible from Earth. What we see as a bright comet streaking across the sky is not a new creation. It is ancient, older than Earth's continents, older than the oceans, older than life itself. It has traveled from the most distant edge of the sun's influence, carrying material untouched since the birth of the solar system. In this way, the Oort Cloud is not just a boundary. It is a storage vault, a frozen archive of primordial matter. Scientists believe that studying these comets gives us direct access to the chemistry of the early solar system. They contain organic compounds, water ice, carbon molecules. Some theories suggest that comets from this region may have helped deliver water and organic material to early Earth. If true, then fragments from the Oort Cloud may have contributed to the conditions that allowed life to begin. This means the outermost region of our solar system may be connected to the origin of biology itself. Now consider the environment inside the cloud. There is no sunlight worth mentioning, no warmth, no atmosphere. Temperatures hover just above absolute zero. Objects there are locked in deep freeze. Movement is slow. Orbital periods are enormous. Some objects take millions of years to complete a single orbit. Time behaves differently here. Not relativistically, but experientially. Nothing changes quickly. Nothing evolves rapidly. The region is almost timeless, a place where the early solar system still exists in frozen form. And yet, this region is not isolated. It is constantly influenced by the galaxy. Our solar system does not sit still. It moves around the center of the Milky Way. As it does, it passes through different stellar neighborhoods. Some regions are crowded with stars, others are emptier. Each time the sun passes near another star, the outer cloud feels it. Gravity reaches out, tugging gently on distant objects, changing orbits, sending comets inward. Over billions of years, this slow interaction reshapes the cloud continuously. It is not static, it is dynamic on cosmic timescales. There is also evidence that the Oort Cloud may not be uniform. Scientists believe there may be an inner cloud and an outer cloud. The inner region is more tightly bound to the sun. The outer region is more loosely held. Objects in the outer cloud are closer to being lost to interstellar space. One strong gravitational encounter could eject them forever. This means the Oort Cloud is slowly leaking material. Over time, some objects escape, some become comets, some fall inward and are destroyed, some are captured by other stars. The cloud is not permanent. It is a temporary structure on billion-year timescales. Now imagine standing at the edge of this region. If you could travel there, if you could look back toward the sun, you would see it as a bright star, surrounded by darkness. The planets would be invisible. Earth would be lost in the glare. From this distance, our entire civilization would be nothing more than a faint dot. The solar system would look small, fragile, isolated, floating alone in a sea of stars. And yet, even here, the sun still holds on. Its gravity still reaches. Its influence still defines what belongs to the solar system and what does not. This makes the Oort Cloud the true outer frontier of our star's domain. Not Pluto, not the Kuiper Belt, but this distant, invisible shell, a boundary where the solar system slowly dissolves into the galaxy. And this is only the beginning, because the Oort Cloud is not just a quiet storage of ice and rock. It is also a place of danger, a region sensitive to stellar encounters, a structure that records the sun's journey through the Milky Way, a reminder that our solar system is not isolated. It is part of a much larger cosmic environment. Next, we will explore how passing stars, galactic tides, and cosmic motion shape this hidden shell, and how the Oort Cloud reveals the long history of the sun's movement through space. The Oort Cloud does not exist in isolation. It is shaped by motion, because the sun is not standing still. Right now, at this very moment, our entire solar system is moving through the Milky Way galaxy at more than 200 kilometers per second. We orbit the galactic center once every 230 million years. During that journey, we pass through different regions of the galaxy. Some are dense with stars, some are quieter, some contain clouds of gas and dust. And every time the sun changes its galactic neighborhood, the outer edge of the solar system feels it. The planets barely notice, but the Oort Cloud does. Because at these extreme distances, gravity becomes fragile. The sun's grip is weak. A passing star does not need to come close to Earth to influence the cloud. It only needs to pass within a few light years. That may sound far, but in cosmic terms, that is a close encounter. When another star passes nearby, its gravity reaches outward like invisible fingers. It tugs on the outer cloud, not violently, not dramatically, but enough to disturb ancient orbits, enough to send objects drifting inward, enough to reshape the structure slowly over millions of years. Astronomers believe that many of the long-period comets that enter the inner solar system are triggered by these stellar encounters. A star passes nearby, the cloud responds, and thousands of years later, a comet appears near Earth. This means that when you see a bright comet in the sky, you may be witnessing the aftermath of a stellar flyby that happened millions of years ago. The cause and the effect are separated by enormous stretches of time. This is how the Oort Cloud operates, slowly, quietly, across geological and cosmic timescales. There is another force acting on the cloud. It does not come from individual stars. It comes from the galaxy itself. The Milky Way exerts what astronomers call galactic tides. Just as the moon creates tides in Earth's oceans, the galaxy creates gravitational tides that stretch and compress the solar system. Near the planets, this effect is negligible, but far away, in the Oort Cloud, it becomes significant. The galactic gravitational field pulls unevenly on different parts of the cloud. It gently reshapes the distribution of objects. It alters orbital inclinations. It changes long-term stability. Over billions of years, this steady influence has helped transform the original scattered debris into the spherical shell we infer today. The cloud is not frozen in one shape. It breathes, it shifts, it evolves. Now consider what this means for the history of the solar system. Every star has its own Oort cloud. Every planetary system that formed giant planets likely scattered debris outward. This suggests that the Milky Way is filled with invisible halos of frozen material, trillions upon trillions of icy objects drifting between stars. Some belong loosely to their parent systems, Others have been ejected entirely. Interstellar space is not empty. It is populated with orphaned worlds, free-floating debris, remnants of planetary formation. This also means that the Oort Cloud may contain objects that did not originate here. During close stellar encounters in the distant past, some debris may have been exchanged between star systems, captured, transferred, trapped by gravity. If this is true, then the Oort Cloud is not just a local archive. It may contain material from other solar systems, fragments of alien planetary nurseries, pieces of distant stellar histories, hidden in the dark, waiting. Now think about scale again. The inner solar system fits comfortably inside the orbit of Jupiter. Even Neptune, the farthest planet, is only 30 astronomical units from the Sun. The Kuiper Belt extends to about 50 astronomical units. The inner edge of the Oort Cloud begins thousands of astronomical units away. The outer edge may reach 100,000 astronomical units. This means the vast majority of the solar system's volume is occupied by the Oort Cloud. Almost all of the Sun's gravitational domain lies in this invisible region. When people imagine the solar system, they imagine planets, but planets occupy only the inner core. The true solar system is mostly empty space filled with faint, distant debris, a giant, ghostly sphere. Now imagine a spacecraft traveling outward, past Mars, past Jupiter, past Saturn, past Neptune. It leaves the planetary region behind. The Sun shrinks. The stars remain fixed. Eventually, Pluto becomes just another point of light. Then the Kuiper Belt fades. The density of objects drops dramatically. Space becomes darker, quieter. But the journey is far from over. Thousands of years pass. The spacecraft continues outward, slowly entering the inner Oort Cloud. Here, the distances between objects are enormous. Even though there may be trillions of bodies, they are spread across such a huge volume that collisions are extremely rare. Most objects never interact. They drift in isolation, frozen, silent, orbiting slowly around the Sun. From this distance, the Sun looks like a bright star, but it is no longer dominant. Nearby stars appear brighter. The influence of the galaxy becomes noticeable. The solar system begins to blend into the Milky Way. This is where the concept of home becomes ambiguous. Is this still part of the solar system? Or is it already interstellar space? The boundary is not sharp. It is gradual. The Sun's gravity weakens slowly with distance. There is no wall, no border marker, just a fading influence. At some point, the Sun can no longer hold on. Objects drift away permanently. They become part of the galaxy. This means the solar system is slowly losing mass. Not dramatically, not suddenly, but continuously. Over billions of years, the Oort Cloud is eroded, stripped away by passing stars and galactic tides. The Sun's gravitational domain shrinks. Its outer shell becomes thinner. This process has been happening since the solar system formed. It will continue long after Earth is gone, long after the Sun becomes a red giant, long after human civilization has vanished. Now consider the implications. The Oort Cloud is a record of the Sun's galactic journey. Its shape, density, and structure reflect the environments the Sun has passed through. Dense star clusters in the early Milky Way, quiet regions of space, spiral arm crossings. Each left subtle fingerprints on the cloud. By studying comets and modeling the cloud, scientists can reconstruct parts of the Sun's past. They can infer where the solar system may have formed, what kind of stellar neighborhood it was born into, how violent the early galaxy may have been. This makes the Oort Cloud not just a storage of debris, but a historical archive, a cosmic memory bank. Now think about the future. The Sun will not remain in its current orbit forever. Over billions of years, gravitational interactions within the Milky Way will slowly change its trajectory. The galaxy itself will evolve. Stars will move. Clusters will disperse. Eventually, the Milky Way will collide with the Andromeda galaxy. When that happens, stellar orbits will be rearranged. The Oort Cloud will be violently disturbed. Many objects will be stripped away. Some will be captured by other stars. Others will be thrown into intergalactic space. The solar system will not remain isolated. It will be reshaped by galactic evolution. Even before that collision, smaller encounters will continue to occur. Passing stars will keep disturbing the cloud, sending new waves of comets inward, triggering distant orbital changes. The Oort Cloud will remain active, not visibly, not dramatically, but persistently. And this has consequences closer to home, because some of those incoming comets eventually cross Earth's orbit. Throughout geological history, comet impacts have occurred. Some may have delivered water, some may have caused mass extinctions. The outermost region of the solar system is connected to life and death on Earth. Events happening tens of thousands of astronomical units away can influence the inner planets millions of years later. This connection across vast distances and timescales is one of the most remarkable features of the solar system. Everything is linked. The Sun, the planets, the distant cloud, the galaxy, all part of one gravitational system. And yet, despite its importance, the Oort Cloud remains unseen. We infer it, we model it, we calculate its effects, but we have never directly observed its structure. No probe has crossed it, no camera has photographed it. It exists as a ghost structure, known only through its influence. This makes it one of the largest known structures in our cosmic neighborhood that we have never visited. A reminder that even in our own solar system, vast regions remain unexplored. And the deeper we look, the more we realize how incomplete our understanding still is. Next, we will move deeper into the internal structure of the Oort Cloud itself, exploring its inner and outer regions, its stability, and the hidden populations of objects that quietly orbit at the very edge of the Sun's reach. The Oort Cloud is not a single uniform structure. It is layered, diffuse, gradual, more like a fading mist than a solid boundary. Scientists divide it into two main regions, an inner cloud and an outer cloud. Together, they form the largest gravitational structure connected to the Sun. The inner region is sometimes called the Hills Cloud. It begins thousands of astronomical units from the Sun. Here, objects are still relatively tightly bound. The Sun's gravity is weak but steady. Orbits are long but stable. Many of these objects may never become comets. They remain frozen in distant loops, circling the Sun once every hundreds of thousands or even millions of years. This inner cloud is thought to act as a reservoir, a buffer zone. When the outer cloud is disturbed by passing stars or galactic tides, objects may fall inward and settle temporarily into this inner region. From here, Some will eventually be nudged closer to the Sun. Others will remain locked in distant orbits for billions of years. The outer cloud lies farther out, much farther. Here, the Sun's gravitational influence becomes fragile. Objects are only loosely bound. A small perturbation can change everything. A distant stellar flyby, a shift in the galactic gravitational field, a subtle tidal force. Any of these can send an object drifting inward or eject it completely. This region is the primary source of long-period comets. When a comet arrives from the farthest reaches of space, it almost always traces its origin back to this outer shell. These objects are among the most ancient materials in the solar system. They formed in the cold outskirts of the early protoplanetary disk. They were scattered outward before the planets fully settled into stable orbits. They have remained frozen ever since, preserved in darkness, unaltered by solar radiation, unchanged by planetary geology. In many ways, they are time capsules, carrying the chemistry of the primordial solar nebula. Inside them are water molecules older than Earth's oceans, carbon compounds that formed before life existed, dust grains that predate the formation of planets. When one of these objects enters the inner solar system, it undergoes a violent transformation. As it approaches the Sun, heat penetrates the surface. Ice sublimates directly into gas. Jets of material erupt from the nucleus. Dust is lifted into space. A glowing coma forms. Solar radiation pressure pushes particles outward, creating the iconic comet tail. What was once a silent frozen relic becomes a bright, dynamic object visible from Earth. But this transformation is destructive. Each pass near the Sun strips material away. Some comets break apart completely. Others gradually fade after repeated visits. The Oort Cloud supplies new comets, but it is not infinite. Over billions of years, the population slowly decreases. Some objects are lost inward. Some are ejected outward. The cloud slowly thins. This gradual depletion is part of the long-term evolution of the solar system. Nothing remains static forever. Now consider the orbital dynamics inside the cloud. Unlike planets, which orbit in nearly circular paths, Oort Cloud objects follow extreme trajectories. Their orbits are highly elongated. They travel enormous distances from the Sun before returning. Some spend nearly their entire orbital period far beyond the planetary region, only briefly passing through the inner solar system before being flung outward again. Others are deflected into hyperbolic paths and never return. The geometry of these orbits reveals the influence of the galaxy. Objects are not confined to the plane of the planets. They arrive from every direction. Above the ecliptic, below it, from random angles. This isotropic distribution is one of the strongest pieces of evidence for a spherical cloud. It shows that the source region surrounds the Sun in all directions, not just along the planetary disk. This spherical shape also provides clues about the Sun's early environment. Astronomers believe the Sun formed inside a dense star cluster. In such environments, close stellar encounters are common. These early interactions would have helped scatter debris outward. They would have shaped the initial structure of the cloud. They may have contributed to capturing material from neighboring systems. As the Sun eventually drifted away from its birth cluster, the frequency of close encounters decreased. The cloud stabilized, but the imprint of those early interactions remains, encoded in the distribution of distant objects. Now imagine the energy balance at these distances. An object in the outer cloud moves extremely slowly. Orbital speeds are measured in tens of meters per second, not kilometers per second like planets. Gravity is weak. Acceleration is minimal. Small forces matter. Radiation pressure, passing interstellar gas, magnetic fields. Over long periods, even subtle influences can change trajectories. This makes the outer cloud a sensitive detector of galactic conditions, a kind of gravitational antenna, responding to the environment through slow motion. There is also another possibility. Some researchers have proposed that the cloud may contain objects much larger than typical comets, dwarf planet-sized bodies, hidden worlds, large icy planets that were scattered outward during the chaotic early stages of planet formation. If such objects exist, they would be extremely difficult to detect. They reflect little light, they move slowly, they are far away, but their gravitational influence could subtly affect comet orbits. Some anomalies in long-period comet trajectories have led to speculation about massive, unseen objects lurking in the distant cloud. These ideas remain controversial, but they highlight how little we truly know about this region. The Oort Cloud remains one of the least explored components of the solar system. It is vast, it is distant, it is invisible, and yet it plays an active role in shaping the inner solar system. It feeds comets, it responds to stellar encounters, it evolves with the galaxy. Now think about timescale again. Earth's geological history spans billions of years. Human history spans thousands. But the processes shaping the Oort Cloud operate on even longer scales. Orbital periods measured in millions of years. Galactic cycles lasting hundreds of millions. Cloud evolution spanning the entire lifetime of the Sun. This means that when we observe the cloud indirectly, we are seeing the result of cumulative cosmic processes, not short events, not sudden changes, but slow gravitational sculpting across deep time. This perspective changes how we understand the solar system. It is not just a static arrangement of planets. It is a living gravitational system, constantly interacting with the galaxy, constantly evolving, constantly reshaping itself. And yet, despite this complexity, the cloud remains stable enough to persist for billions of years. It does not collapse, it does not disperse instantly. It survives because of balance between solar gravity, galactic tides, stellar perturbations, and orbital dynamics, a fragile equilibrium. Now consider what happens when this balance is disrupted. A close stellar flyby could strip away a significant portion of the cloud. Such events may have happened in the distant past, in dense star-forming regions. During the Sun's early life, some models suggest that the Oort Cloud may have been much larger in the past, more massive, more populated, and that it has gradually lost material over time. If true, then what we see today is only a remnant, a reduced version of a once even larger structure. This loss continues today, slowly, quietly, but continuously. The cloud is slowly eroding, and as it erodes, the solar system becomes more isolated. Its outer halo thins, its gravitational reach shrinks. The boundary between the Sun and the galaxy becomes sharper, more defined. This process will continue for billions of years until eventually the Sun's outer cloud may be stripped almost entirely, leaving behind only the planets and inner debris. At that point, the solar system will be far smaller than it is today, but that future lies far ahead. Long after Earth is uninhabitable, long after the Sun has changed. For now, the Oort Cloud remains, a vast hidden shell, a frozen archive, a gravitational frontier, and a reminder that even in our own cosmic backyard, most of what exists remains unseen. Next, we will explore how the Oort Cloud connects directly to comet storms, mass extinction events, and the deep relationship between distant space and life on Earth. From Earth, comets appear rare. They arrive unexpectedly. They brighten the sky for a few weeks, then they disappear again. But on cosmic timescales, comet activity is not random. It follows patterns, waves, cycles, and many of these cycles begin far beyond the planets, inside the distant shell of the Oort Cloud. When a passing star disturbs the outer cloud, the effects are not immediate. Nothing dramatic happens right away. Instead, small orbital changes ripple through the cloud. Objects that were once stable begin drifting inward, slowly, quietly, over tens of thousands of years, over hundreds of thousands of years. Eventually, these disturbances reach the inner solar system. And when they do, the result can be a surge in comet activity. Astronomers call these periods comet showers, not storms in the traditional sense, but long-lasting increases in the number of comets entering the planetary region. During these times, Earth and the inner planets face a higher probability of impacts. The sky becomes more active, more dangerous, more unpredictable. This connection between distant stellar encounters and inner solar system events reveals something important. The Oort Cloud is not just a passive reservoir. It is an active participant in shaping planetary history. Now consider Earth's past. Our planet has experienced multiple mass extinction events. Some were caused by volcanic activity, some by climate shifts. But at least one major extinction is strongly linked to an asteroid or comet impact. 66 million years ago, a massive object struck Earth near what is now the Yucatan Peninsula. The impact released energy equivalent to billions of nuclear bombs. It triggered global fires, darkened the atmosphere, collapsed ecosystems, and ended the reign of the dinosaurs. The exact origin of that impactor is still debated, but some models suggest that comet showers from the Oort Cloud may increase the likelihood of such catastrophic events. When the cloud is disturbed, more long-period comets enter the inner solar system. Some cross Earth's orbit, most miss, but occasionally one does not. This means that events happening tens of thousands of astronomical units away can shape the biological history of a planet. Life on Earth may have been influenced by gravitational interactions far beyond the planets. The solar system is connected across enormous distances. Now imagine the scale of these comet reservoirs. Trillions of objects, each with the potential to become an impactor under the right conditions, but also each carrying water, organic molecules, and primordial material. Comets are not only destructive, they are also carriers of ingredients necessary for life. Many scientists believe that early Earth received a significant portion of its water from cometary impacts. During the early solar system, Earth was hot and volatile. water could not remain stable on the surface. As the planet cooled, impacts delivered ice and organic compounds. These materials accumulated. They formed oceans. They provided chemical building blocks. In this way, the Oort Cloud may have contributed to the habitability of Earth. It may have helped create the conditions necessary for life. The same region that sends destructive impactors also delivers life-sustaining material. Creation and destruction emerge from the same distant source. Now think about the long-term rhythm. Over hundreds of millions of years, the solar system moves through different regions of the galaxy. Dense star clusters, spiral arms, gas-rich zones. Each passage increases the likelihood of stellar encounters. Each encounter increases disturbances in the cloud. This creates a rough periodicity in comet influx. Not precise, not clock-like, but statistically significant. Some researchers have even suggested correlations between mass extinction events and the Sun's oscillation through the galactic plane. As the solar system moves above and below the dense midplane of the Milky Way, gravitational disturbances increase. More comets are sent inward. Impact rates rise. Life on Earth may be indirectly influenced by the structure of the galaxy itself. This idea is still under investigation, but it highlights how deeply interconnected cosmic systems are. Local biology, planetary geology, solar system dynamics, galactic structure, all tied together by gravity and motion. Now consider the perspective of the Oort Cloud itself. From within the cloud, the inner solar system is just a distant glow. The planets are invisible. Earth is unobservable. Yet objects in this region can eventually shape planetary history. This is the paradox of scale. Small frozen bodies, far away and insignificant in appearance, can influence the fate of worlds. This also raises questions about planetary defense. We track near-Earth asteroids closely. We monitor potential impact threats from the asteroid belt. But long-period comets are more difficult. They appear with little warning. They move quickly when near the Sun. Their orbits are steep and unpredictable. They can arrive from any direction. This makes them harder to detect early, harder to deflect, harder to prepare for. The source of these objects lies in the most distant part of the solar system, a region beyond direct observation. This means that planetary safety depends partly on processes happening far beyond our current ability to monitor. Another layer of uncertainty, another reminder of how small our control truly is. Now imagine the far future. As the Sun ages, its luminosity will increase. The inner planets will heat up. Earth will become uninhabitable long before the Sun becomes a red giant. But the Oort Cloud will still exist, frozen, unaffected by the slow warming of the inner solar system. When the Sun eventually enters its red giant phase, it will lose a significant portion of its mass. Solar winds will carry material outward. The gravitational hold of the Sun will weaken. This will destabilize the Oort Cloud. Many objects will be released. Some will be ejected into interstellar space. Others will fall inward. Comet activity may spike dramatically during this period. The dying Sun will trigger one final wave of motion across its outer halo. Even in death, the star will reshape its distant shell. This means the Oort Cloud is not just a relic of the past. It is also a participant in the future evolution of the solar system. It will respond to the Sun's transformation. It will reshape itself one last time. Now step back and consider the larger picture. The Oort Cloud connects the inner planets to the galaxy. It acts as an interface, a transition zone, a bridge between stellar and interstellar space. It responds to galactic tides. It records stellar encounters. It feeds material inward. It leaks material outward. It links planetary history to galactic motion. This makes it one of the most important structures in understanding how planetary systems interact with their cosmic environment. And yet, it remains invisible. We infer it through mathematics, through orbital models, through comet statistics, through indirect evidence. This invisible structure shapes visible events, a hidden engine operating far beyond the planets. Now imagine future exploration. One day, humanity may send probes designed specifically to study this region, not with current technology, not with chemical rockets, but with advanced propulsion, light sails, nuclear engines, interstellar precursors. Such missions would take centuries, maybe millennia, but they would provide direct measurement of a region that has remained theoretical for decades. They would allow us to confirm the structure, map the distribution, measure the composition, and finally see the outer boundary of our solar system directly. Until then, the Oort Cloud remains an unseen frontier, a distant shell shaping the past and future of our planetary system. Next, we will move deeper into the question of how the Oort Cloud formed in the first place, and what its existence tells us about the chaotic birth of the Sun and the early violence of planetary formation. The greatest challenge of the Oort Cloud is not its distance, it is its invisibility. Unlike planets, it does not reflect enough sunlight to be seen directly. Unlike nebulae, it does not glow. Unlike stars, it does not produce energy. It exists in darkness, and yet scientists attempt to study it anyway. They do this by watching what escapes from it. Every long-period comet that enters the inner solar system becomes a messenger, a fragment of the distant cloud, carrying information about its origin. When astronomers track the orbit of a comet, they look backward in time. They calculate where it came from. They analyze its inclination, its velocity, its trajectory. When these paths are traced far enough, patterns emerge. Comets arrive from all directions, not just the plane of the planets, not just the Kuiper Belt. This isotropic distribution points to a spherical source, a distant shell, the Oort Cloud. This indirect method is one of the few tools scientists have. Another method involves computer simulations. Astronomers recreate the early solar system using physics models. They simulate planet formation, planetary migration, gravitational scattering, stellar encounters, galactic tides. They allow these virtual solar systems to evolve over billions of years. When the simulations produce a distant spherical cloud similar to what we infer from comet observations, confidence increases. Theoretical models and observational data align. Together, they build a picture of a structure that cannot be seen. But even with these tools, uncertainty remains. We do not know the exact size of the cloud. We do not know its precise mass. We do not know how many objects it contains. Estimates range widely. Some models suggest hundreds of billions of objects. Others suggest trillions. The true number may be even higher. The cloud may contain more mass than the asteroid belt, possibly more than the Kuiper Belt, spread thinly across an enormous volume. This makes density extremely low, but total content enormous. Now consider detection attempts. Astronomers have tried to observe distant Oort Cloud objects directly. Occasionally, extremely distant objects are discovered beyond the Kuiper Belt. Some have highly elongated orbits. Others show unusual inclinations. These objects provide clues, but they represent only the inner fringe of the cloud. The majority remains too faint, too slow-moving, too distant to be detected with current technology. Even the most powerful telescopes struggle. Light reflected from these objects is incredibly weak. Their apparent motion across the sky is tiny. They blend into the background. This makes direct mapping nearly impossible. For now, future observatories may change this. Next-generation telescopes will be more sensitive. They will observe deeper into space. They may detect faint, distant bodies previously invisible. This could allow astronomers to identify populations of inner Oort Cloud objects. Not the full structure, but glimpses, fragments of the whole. Now think about space missions. No spacecraft has ever reached the Oort Cloud. Voyager 1 and Voyager 2 are the farthest human-made objects. They are traveling at about 17 kilometers per second. At this speed, it will take them tens of thousands of years to reach the inner edge of the cloud, and even longer to cross it. Human lifetimes are too short. Technological eras are too brief. Direct exploration is beyond current planning horizons, but that does not mean it will never happen. Future propulsion systems may change this. Nuclear propulsion, fusion drives, light sails powered by lasers. These technologies could drastically reduce travel times. A probe designed specifically to study the outer solar system could reach the inner cloud within centuries instead of millennia. Still long, but no longer unimaginable. Such a mission would face extreme challenges: power generation, communication delays, navigation in deep space, autonomous operation. But the scientific payoff would be enormous: direct measurement of primordial material, mapping of distant debris, confirmation of theoretical models, understanding the true structure of our solar system's outer boundary. Now consider another approach: interstellar objects. In recent years, astronomers have detected objects passing through the solar system that did not originate here. Oumuamua was the first known interstellar visitor detected. It entered the solar system from outside, passed close to the Sun, then left. Its trajectory confirmed it was not bound to the Sun. It came from another star system. This discovery confirmed something important. Interstellar space is filled with wandering debris, objects ejected from Oort clouds of other stars, or from planetary systems undergoing formation and destruction. If interstellar objects pass through our system, then the reverse is also true. Objects from our Oort cloud are constantly being lost to the galaxy. The cloud is not closed. It exchanges material with interstellar space. This means the Oort cloud is not just part of the solar system. It is part of a larger galactic ecosystem. Material circulates. Systems exchange debris. Stars influence each other indirectly through gravitational interactions. This creates a slow mixing of material across the galaxy. Over billions of years, the Milky Way becomes chemically interconnected. Now think about how this challenges our idea of boundaries. Where does the solar system end? At the heliopause, where the solar wind meets interstellar space. At the Kuiper Belt, at the outer edge of the Oort cloud. There is no single answer. Different definitions apply to different phenomena. The heliosphere defines the boundary of solar wind influence. The gravitational domain extends much farther. The Oort cloud marks the farthest region where objects remain loosely bound to the Sun. Beyond that lies interstellar space. But the transition is gradual, not sharp. The solar system fades into the galaxy. It does not end abruptly. This concept of fading boundaries is common in astrophysics. Galaxies fade into intergalactic space. Star clusters fade into stellar populations. Everything blends. Nothing is isolated. Now consider the philosophical implications. We often think of our cosmic home as compact, neat, organized, but the true structure is vast, diffuse, uncertain. Most of what belongs to the solar system is invisible. Most of its volume is empty. Most of its mass is locked in distant frozen debris. Our everyday perception is centered on the inner region, but the reality extends far beyond what we experience. This changes how we define neighborhood. The Sun's neighborhood is not just planets. It includes a cloud that stretches nearly to other stars. This makes our local environment far larger than intuition suggests. Now imagine a map of the solar system drawn to scale. The planets would cluster near the center. The Kuiper Belt would appear as a thin ring. And then, nothing. A vast empty region. And then, far away, a faint haze representing the Oort cloud. The map would be mostly empty space, but that empty space would contain the largest structure tied to the Sun. This visual contrast highlights the strange geometry of planetary systems: dense cores, diffuse halos, sharp inner activity, silent outer boundaries. Now consider future discoveries. If astronomers detect massive distant objects in the inner cloud, if they map the distribution of comet sources more precisely, if they track stellar flyby effects in real time, our understanding of the cloud will improve. We will refine models. We will reduce uncertainty. We will see the invisible more clearly. But some aspects may always remain theoretical because of distance, because of time, because of technological limits. The Oort cloud may never be fully mapped, never completely understood. It may remain partially hidden, a permanent frontier, and perhaps that is fitting, because the Oort cloud represents the edge of what the sun controls, the fading influence of a star, the transition between system and galaxy, between home and deep space, between order and cosmic chaos. Next, we will explore what happens to the Oort cloud as the sun ages, and how the final stages of the sun's life will reshape this distant shell forever. The sun will not remain the star we know forever. Right now, it appears stable, calm, predictable. But this stability is temporary. Deep inside its core, hydrogen is being converted into helium. Every second, relentlessly. This process has powered the sun for billions of years, and it will continue for billions more. But eventually, the fuel will change. When the core hydrogen is exhausted, the balance that keeps the sun stable will break. Gravity will begin to compress the core. Temperature will rise. Pressure will increase. And the sun will enter a new phase of its life. It will expand, slowly at first, then dramatically. The sun will become a red giant. Its outer layers will swell outward, engulfing Mercury, possibly Venus, and maybe even Earth. But far beyond this violent transformation, something else will be happening. Something quieter, something more subtle. The Oort cloud will begin to feel the change. As the sun expands, it will lose mass. Stellar winds will grow stronger. Material will be pushed outward. The sun's gravitational pull will weaken. This loss of mass does not happen all at once. It happens gradually. But even small changes in mass have enormous consequences at great distances. For the planets, the effect will be noticeable. Orbits will slowly expand outward. But for the Oort cloud, the effect will be dramatic. Because at the outer edge of the sun's gravitational domain, objects are barely held in place. When the sun loses mass, its ability to hold onto distant objects decreases. The gravitational boundary shrinks. The Oort cloud becomes unstable. Objects that once orbited safely will begin to drift away. Some will be released into interstellar space. Others will fall inward. This process will not be gentle. It will trigger a massive redistribution of material, a final reshaping of the solar system's outer halo. During the red giant phase, the sun will shed a large fraction of its mass. This material will form a planetary nebula, a glowing shell of gas expanding outward into space. Beautiful, colorful, short-lived, but powerful. As this shell expands, it will pass through regions once occupied by the inner Oort cloud. Radiation will increase. Shock waves will propagate. Local environments will change. Objects that have remained frozen for billions of years will suddenly be exposed to intense energy. Some will heat up. Some will fragment. Some will be pushed onto new trajectories. The quiet stability of the cloud will be replaced by chaos. Now imagine this moment. For billions of years, the cloud has remained almost unchanged. Then, in a relatively short astronomical period, everything shifts. Orbits destabilize. Comets are released. The solar system experiences a final wave of inbound material. A late comet storm. One last delivery of ancient debris. But this time, Earth will no longer be here. The inner planets will be uninhabitable. The oceans will be gone. The atmosphere will be stripped. Life, if it still exists anywhere in the system, will have retreated or vanished. The comet storm will unfold in silence. No observers, no witnesses, just gravitational mechanics playing out across deep time. Eventually, the sun will shed its outer layers completely. The core will collapse into a white dwarf, a dense remnant, roughly the size of Earth, containing about half the original mass of the sun. The solar system will be transformed, no longer dominated by a massive star, but by a small, faint, stellar corpse. This change will permanently alter the structure of the Oort cloud. Many objects will be lost forever. The gravitational hold of the white dwarf will be far weaker than that of the original sun. The cloud will thin dramatically. Its outer regions will disperse. Only the innermost objects may remain loosely bound. The solar system will shrink, not physically, but gravitationally. Its sphere of influence will contract. What remains will be a ghost version of the system we know today. A white dwarf at the center. Remnant planets on expanded orbits, scattered debris drifting through deep space, and fragments of the once massive cloud slowly dissolving into the galaxy. Now, consider the timescale. The sun will become a red giant in about 5 billion years. The transformation will unfold over hundreds of millions of years. From the perspective of the Oort cloud, this is sudden, an abrupt event after billions of years of stability, a shock to a frozen system. This shows that even the most stable cosmic structures are temporary. Nothing lasts forever, not planets, not stars, not distant clouds of debris. Everything evolves, everything changes, everything eventually dissolves. Now imagine a distant observer in the far future, perhaps from another star system, looking toward the remnants of our solar system. They would not see planets, they would not see oceans, they would not see life. They would see a faint white dwarf, surrounded by a thin halo of debris, a remnant cloud, a faint trace of what once existed. They would have no way of knowing that this system once hosted living organisms, civilizations, technology, article history, all erased, reduced to gravitational leftovers. This perspective is unsettling, but it is also honest. The universe does not preserve stories. It preserves mass and energy. Everything else fades. Now return to the present. Right now, the Oort cloud exists in a quiet balance. The sun is stable. The galaxy is calm. The cloud drifts silently. But this stability is temporary. It is part of a much larger cosmic cycle. Formation, evolution, disruption, dissolution. The Oort cloud is not the end of the story. It is a phase, one stage in the long life of a planetary system, a stage that bridges youth and old age, between formation and destruction. Now consider how rare this moment is. We live at a time when the sun is stable, when Earth is habitable, when the Oort cloud is intact, when the solar system still resembles its original structure. This window will not last forever. It is a brief moment in cosmic history, a temporary arrangement, a snapshot. We are witnessing the solar system during its middle age, not its birth, not its death, but its long, stable plateau. And far beyond our awareness, the distant cloud waits, frozen, silent, carrying the memory of the past and the seeds of the future. Next, we will step even farther outward, beyond the Oort Cloud itself, and explore how this hidden shell connects the solar system to interstellar space, neighboring stars, and the vast environment of the Milky Way galaxy. Beyond the outer edge of the Oort Cloud, the sun's influence begins to fade completely. There is no sharp boundary, no wall, no visible line in space. Instead, gravity weakens gradually. Objects drift more freely. Orbits become unstable, and eventually, the solar system dissolves into the background of the Milky Way. This region marks the transition between belonging and isolation, between what is still part of the sun's domain and what has become truly interstellar. At these distances, the galaxy becomes the dominant force. The gravitational pull of the Milky Way outweighs the influence of the sun. Stars pass at vast distances, yet their combined gravitational effects accumulate. Gas clouds drift through. Cosmic radiation becomes more intense. The environment changes. The solar system no longer exists as a self-contained structure. It becomes part of a larger flow of galactic material. This is where the Oort Cloud connects to the wider universe, not just physically, but dynamically. Material from the cloud escapes outward. At the same time, interstellar debris occasionally drifts inward. The boundary is porous, open, exchanging matter slowly over billions of years. Now imagine a single object at the very edge of the cloud. It orbits the sun extremely slowly. Its motion is delicate, balanced between competing gravitational influences. A small change in velocity can determine its fate, remain bound, or drift away forever. When a passing star moves through this region, even at a distance of several light years, its gravity can tip the balance. The object's orbit stretches, it becomes unstable, and eventually it escapes. Once free, it becomes part of interstellar space, no longer belonging to any star, drifting through the galaxy as a wandering fragment of ancient planetary systems. These free-floating objects are not rare. Astronomers now believe that the Milky Way contains enormous numbers of rogue planets, icy bodies, and debris. Some were ejected during planet formation. Others were stripped from distant Oort clouds. Together, they form a hidden population moving silently between stars. This means that our solar system is not isolated. It is constantly exchanging material with the galaxy, losing fragments, gaining visitors, slowly participating in a massive cosmic circulation. Now think about what this implies for the long history of matter. Atoms that formed in the early universe became part of stars. Stars created heavier elements. Those elements formed planets. Planets scattered debris. Debris entered Oort clouds. Some of that debris escaped, and eventually it may become part of another system. Material migrates across cosmic distances, not quickly, not dramatically, but persistently, over billions of years. This creates a slow mixing of the galaxy, a redistribution of matter across stellar systems. In this sense, the Oort cloud is not just a boundary, it is a gateway, a region where material transitions from being solar-bound to becoming galactic. Now imagine the solar system passing through different galactic environments: spiral arms, dense star clusters, regions rich in gas and dust. Each environment affects the cloud differently. In dense regions, stellar encounters become more frequent. The cloud is disturbed more often. Material is stripped away faster. In quieter regions, the cloud remains more stable. The Sun's current location in the Milky Way is relatively calm. We are not in a dense star-forming region. We are not near the galactic center. This has allowed the Oort Cloud to remain intact for billions of years. But this will not always be the case. Over long timescales, the Sun's orbit will change. It will drift inward and outward. It will cross spiral arms. It will encounter different gravitational environments. Each transition will reshape the cloud. Some parts will be lost. Others will be compressed. The structure will continue evolving. Now consider how this affects the concept of home. We often think of the solar system as a fixed location, a stable address in the galaxy. But in reality, it is moving, carrying its planets, debris, and distant cloud along a galactic orbit. The Oort Cloud travels with the Sun. It is dragged through space, slowly reshaped by the environment it passes through. This means the outermost part of the solar system is constantly exposed to the galaxy. It is the first region to feel changes, the first to respond to new gravitational influences, the first to lose material. In this sense, the Oort Cloud acts as a buffer zone, absorbing external disturbances, protecting the inner planets from direct stellar interactions. Most passing stars affect the cloud first. By the time gravitational effects reach the inner solar system, they are weakened, spread out, diffused. This protective role is subtle but important. It helps maintain long-term stability in the planetary region. Now imagine what would happen if the cloud did not exist. The inner solar system would be more exposed to galactic forces. Stellar flybys would have more direct effects on planetary orbits. The long-term stability of Earth's orbit might be less secure. The existence of this distant halo may contribute indirectly to the long-term habitability of inner planets. Now step back and view the solar system as a whole. At the center is the Sun, surrounded by planets, encircled by belts of debris, wrapped inside a massive invisible shell. And beyond that, the galaxy. Each layer transitions gradually into the next. No sharp borders, only fading influence. This layered structure mirrors patterns seen throughout the universe. Atoms surrounded by electron clouds, stars surrounded by planetary systems, galaxies surrounded by dark matter halos, clusters surrounded by cosmic filaments. Everything exists inside nested structures, each fading into the next. The Oort Cloud fits naturally into this hierarchy. It is the solar system's halo, its outermost extension. Now consider what this tells us about scale. From Earth, the solar system feels enormous. From the Oort Cloud, it feels small. From the galaxy, it is just one star among hundreds of billions. From the universe, it is almost nothing. Perspective changes meaning. Significance depends on scale. Yet within this tiny system, complex processes unfold. Life emerges, civilizations rise, technology develops, all inside a structure that is dwarfed by cosmic distances. The Oort Cloud reminds us of this contrast. It marks how far the Sun's influence reaches, and how quickly that influence fades into insignificance. on galactic scales. Now imagine future human exploration. If humanity survives long enough, if technology advances far enough, there may come a time when probes reach the inner edge of the cloud. They will travel for centuries, communicating with Earth across enormous distances, sending back data about temperature, particle density, and gravitational environment. Such missions would redefine our understanding of local space. They would transform the Oort Cloud from a theoretical concept into a mapped region. But even then, the full structure would remain beyond reach. The outer cloud is simply too large, too distant, too slow to explore completely. Some regions may remain forever unvisited, unmeasured, unknown. This is not a failure of science. It is a consequence of scale. The universe is larger than any civilization can fully explore. There will always be boundaries, always frontiers, always regions that remain unseen. The Oort Cloud represents one of those frontiers, not at the edge of the universe, but at the edge of our own star's domain, a quiet boundary between solar order and galactic freedom. Next, we will step back once more and examine what the Oort Cloud ultimately tells us about the nature of planetary systems, cosmic evolution, and humanity's place inside an ever-changing universe. When scientists speak about the Oort Cloud, they are not just describing a distant region of space. They are describing a memory, a record of the solar system's earliest moments. Every object drifting in that distant shell carries information about how the sun formed, how the planets migrated, and how gravity sculpted matter in the first chaotic era. The cloud is not frozen only in temperature. It is frozen in time. Its objects have remained largely unchanged for billions of years. They have not been melted by stellar heat. They have not been reshaped by geological processes. They have not been recycled through planetary interiors. They remain primitive, untouched, preserved. In this way, the Oort Cloud functions like a cosmic archive, a library of ancient material stored far from the sun. Each comet that falls inward becomes a page from that archive. When it vaporizes near the sun, it releases clues, chemical signatures, isotopic ratios, organic compounds, all revealing details about the environment in which the solar system was born. These measurements allow scientists to reconstruct the early conditions of our cosmic neighborhood, the temperature of the primordial disk, the chemical composition of the nebula, the distribution of volatile elements. Without the Oort Cloud, much of this information would be lost. Now consider what this means for understanding other planetary systems. Astronomers have discovered thousands of exoplanets. Many of them orbit stars very different from the Sun. Hot stars, small red dwarfs, binary systems. Some planetary systems are compact, others are chaotic. Some contain massive gas giants close to their stars. Others show wide, distant orbits. But in many of these systems, scientists suspect similar distant debris clouds may exist. They cannot be seen directly, but their gravitational effects and comet activity may reveal their presence. If Oort clouds are common, then most stars may be surrounded by distant halos of frozen debris. This would mean that planetary systems are not limited to visible planets. They extend far beyond what telescopes currently detect. Each system may have its own hidden boundary, its own reservoir of ancient material, its own distant archive. This changes how we think about planetary architecture. A star system is not just a central star and orbiting planets. It is a layered structure with inner activity and outer preservation, a dynamic core and a frozen halo. Now think about habitability. When scientists search for life elsewhere in the galaxy, they often focus on habitable zones, regions where liquid water can exist on planetary surfaces. But the broader environment matters too. The presence of distant debris clouds may influence impact rates, water delivery, organic material transport, radiation shielding, galactic interaction buffering. All of these factors affect long-term planetary stability. In this sense, the Oort Cloud is part of the habitability story. Not directly, but indirectly. It shapes the environment in which life develops. It influences the frequency of catastrophic events. It contributes to the delivery of life-building materials. It participates quietly in the conditions that allow civilizations to exist. Now, consider the psychological effect of this perspective. We often imagine Earth as isolated, a small blue dot floating alone in space. But in reality, Earth is embedded inside a vast, layered gravitational system, connected to distant debris, connected to galactic tides, connected to passing stars. Our planet is part of a much larger structure than our senses reveal. This realization changes how we understand isolation. We are not alone in space, not because of aliens, but because of physical connections, because gravity links us to distant regions, because matter circulates across cosmic scales, because the solar system itself is part of a larger galactic flow. Now imagine standing on Earth at night, looking up at the stars. You see points of light, but you do not see the vast structure surrounding you. You do not see the Kuiper Belt. You do not see the Oort Cloud. You do not see the invisible boundary where the sun's influence fades. Yet all of it exists around you, above you, below you, in every direction. You are inside a massive gravitational cocoon, one that extends nearly to neighboring stars. This hidden structure challenges our intuitive sense of scale. It forces us to think beyond immediate surroundings, to imagine space not as empty, but as structured, layered, interconnected. Now think about time again. The Oort Cloud has existed for billions of years. It will continue to exist for billions more. Human civilization has existed for only a few thousand. Recorded history covers only a fraction of that. Our entire technological era is shorter than the blink of an eye on cosmic timescales. Yet during this brief moment, we are able to infer the existence of structures that operate on timescales far beyond our own. We use mathematics, physics, observation, inference. We build models of regions we cannot reach. This ability is one of humanity's greatest achievements. We may not travel to the Oort Cloud, but we can understand it. We can map its influence. We can trace its effects. We can reconstruct its origin. In this way, knowledge allows us to transcend physical limits, even when distance prevents direct exploration. Now consider the future of this knowledge. As technology advances, our understanding of distant regions will improve. Better telescopes, better simulations, better detectors, better data analysis. We will refine models. We will reduce uncertainty. We will map more distant objects. We will observe more interstellar visitors. Each new discovery will sharpen the image, but the Oort Cloud will likely remain partly mysterious, because some frontiers cannot be fully crossed. They can only be approached. This is not a weakness of science. It is part of its nature. Science does not eliminate mystery. It reshapes it. It replaces ignorance with deeper questions. The more we learn about the Oort Cloud, the more we realize how complex and dynamic our cosmic environment truly is. Now think about the emotional dimension. There is something poetic about a hidden shell of ancient objects surrounding our star. A silent guardian, a distant archive, a fading boundary between home and the galaxy. It adds depth to our understanding of place. It makes the solar system feel larger, older, more complex, more alive with motion and history. The Oort Cloud reminds us that the universe is not static. Even the most distant, frozen regions are shaped by forces. Gravity never stops working. Motion never truly ends. Everything is always changing, even when change is slow. Now step back once more. Imagine the solar system as a whole. The sun shining at the center, planets circling, asteroids drifting, comets waiting in darkness, a vast cloud surrounding everything, and beyond that, billions of other stars with their own systems, each with their own hidden halos, each with their own cosmic history. Together, they form a galaxy filled not only with stars, but with invisible structures, silent connections, slow exchanges of matter, a living cosmic ecosystem. The Oort Cloud is one piece of that system, small on galactic scales, huge on planetary scales, and deeply connected to the story of our origins. Next, we will bring this journey to its final perspective by stepping back one last time and asking what the existence of the Oort Cloud ultimately tells us about humanity's place in the universe. When we step far enough back, the Oort Cloud stops being just a scientific concept. It becomes a symbol, a reminder of scale, a reminder of distance, a reminder of how small our everyday world is compared to the structures that surround it. From the surface of Earth, the solar system feels enormous. From the perspective of the Oort Cloud, Earth is almost invisible, a faint dot orbiting a distant star. And from the perspective of the galaxy, even the entire solar system is insignificant. One system among hundreds of billions. Yet within this small corner of the universe, consciousness emerged. Life evolved. Intelligence developed. Creatures began asking questions about the cosmos. And eventually, we discovered that our home is surrounded by a vast, invisible shell of ancient material. This realization changes how we define belonging. We are not just inhabitants of a planet. We are inhabitants of a star system. And that star system extends far beyond the planets. It reaches into deep space. It fades slowly into the galaxy. We live inside a structure that is much larger than our senses can perceive. Now consider the contrast. At one extreme, there are human experiences, daily routines, cities, languages, technology. At the other extreme, there are structures like the Oort Cloud, trillions of frozen objects, distances measured in light years, timescales measured in billions of years. Between these extremes lies the full range of cosmic scale, and yet they are connected. The atoms in your body were once part of ancient stars. Some may have traveled through interstellar space. Some may have been part of distant debris clouds. Matter moves, recycles, circulates. What seems separate is part of a continuous process. Now imagine future generations. Perhaps thousands of years from now, perhaps millions. If humanity survives long enough, Our descendants may no longer live only on Earth. They may inhabit other worlds, artificial habitats, deep space colonies. They may send probes far beyond the planets. They may explore the Kuiper Belt. They may approach the inner edge of the Oort Cloud. For them, what is theoretical today may become measurable tomorrow. They may witness directly what we can only infer. But even then, the outer cloud will remain distant, still vast, still slow, still operating on timescales far longer than any civilization. This shows that no matter how advanced technology becomes, there will always be boundaries, not because of failure, but because of scale. The universe is larger than any species can fully explore. There will always be horizons, always unknown regions, always unanswered questions. And that is not a limitation. It is an invitation. It keeps curiosity alive. It keeps exploration meaningful. Now think about the emotional impact of this idea. There is comfort in knowing that the solar system is surrounded by something ancient and quiet, a frozen halo that has existed since the birth of the sun. It creates a sense of continuity, a sense that our world is embedded inside a much older structure, that our present moment is just one frame in a much longer cosmic film. The Oort Cloud has watched the solar system evolve. It was there when Earth formed. It was there when the oceans appeared. It was there when life began. It was there when dinosaurs walked the planet. It was there when humans emerged. And it will remain long after humanity is gone. It does not observe. It does not think, but it persists, a silent witness to cosmic time. Now consider the ultimate fate of the universe. Stars will burn out. Galaxies will drift apart. Energy will spread thin. Even white dwarfs will eventually cool. Black holes will slowly evaporate. Everything will fade. In that distant future, the Oort Cloud will be long gone. Its objects will be scattered, absorbed, recycled. Nothing will remain in its current form. But the story of its existence will remain written in the structure of the universe. Because every structure leaves an imprint. Every process shapes what comes after. Now return to the present one last time. Right now, you are inside this system, inside the gravitational reach of the sun, inside a halo of frozen debris, inside a galaxy filled with stars, inside a universe expanding in all directions. This layered reality is easy to forget. Daily life feels small, local, immediate, but behind every ordinary moment is an extraordinary cosmic context. The Oort Cloud reminds us of that. It reminds us that home is not just Earth. It is not just the solar system. It is part of something much larger, something ancient, something still evolving. And even though we may never see the Oort Cloud directly, even though we may never travel to its farthest reaches, it is still part of us, because it is part of the system that created us. The sun, the planets, the debris, the cloud, the galaxy, all connected, all shaped by gravity, all moving through time together. This is the hidden shell around our solar system. Silent, invisible, vast, and always there. There is one final perspective that changes everything. It is not about distance, not about gravity, not about comets or stars. It is about meaning. Because when we look at the Oort Cloud, we are not only looking outward, we are also looking inward, at the limits of human perception, at the boundaries of knowledge, at the strange relationship between what we can observe and what we must infer. Most of what defines our solar system is invisible. The planets are visible. The sun is visible. But the largest structure connected to our star cannot be seen at all. It exists only through evidence, through motion, through mathematics, through quiet gravitational fingerprints left behind in comet orbit. This reveals something important about the universe. Reality does not require visibility to exist. Most of what shapes cosmic evolution is hidden. Dark matter, dark energy, invisible gas, distant debris, silent forces. The universe is built from things we rarely see, yet they determine everything we experience. Now think about the irony. Human civilization is obsessed with what is close, what is immediate, what is visible. But the most influential processes often happen far away, quietly, slowly, beyond direct observation. The Oort Cloud is a perfect example of this. It does not dominate headlines. It does not appear in night skies. It does not produce dramatic explosions. And yet, it shapes comet activity. It influences planetary safety. It preserves ancient chemistry. It records the birth of the solar system. It connects the sun to the galaxy, all without ever being seen. Now imagine explaining this to someone who lived thousands of years ago, a person who watched comets streak across the sky and believed they were omens. They would never imagine that these glowing visitors originated from a hidden shell tens of thousands of times farther away than the sun. They would never imagine that Earth itself was surrounded by an invisible halo of frozen worlds. And yet today, we understand this, not because we traveled there, but because we learned how to listen to the universe through physics. This is one of the quiet miracles of science. It allows us to understand places we cannot reach, times we cannot witness, structures we cannot see. Now consider the limits of this understanding. Even with modern technology, there are things we may never fully know. We may never map the entire cloud. We may never count all its objects. We may never observe its outer boundary directly. But partial knowledge is not failure. It is the natural state of exploration. Every generation pushes the frontier slightly farther, then passes the responsibility forward. The Oort Cloud reminds us that exploration does not always mean travel. Sometimes it means interpretation, inference, modeling, patience. Now think about scale again. The inner solar system occupies a tiny fraction of the sun's gravitational domain. Everything familiar to us is compressed into a small central region. Beyond that lies emptiness. And beyond that emptiness lies the cloud. Most of the solar system's volume is empty space. But that empty space is structured, organized by gravity, shaped by motion, defined by influence rather than material density. This challenges how we define structure. We tend to think of structure as something solid, something visible. But in astrophysics, structure often means patterns of motion, regions of influence, fields of force. The Oort Cloud is a structure not because it is dense, but because it is bound, because its objects share a common gravitational relationship with the sun. Now imagine removing the sun. Instantly, the cloud would dissolve. Objects would drift away. The structure would disappear. This shows how deeply everything depends on gravitational relationships. Nothing exists independently. Everything is connected through force. Now apply this idea to the larger universe. Galaxies exist because of gravity. Clusters exist because of gravity. Cosmic filaments exist because of gravity. Everything we see is the result of invisible forces shaping matter over time. The Oort Cloud is one small example of this universal pattern. Now think about perspective again. We often describe space as empty, but empty space is not empty. It contains radiation, particles, fields, gravitational influence, invisible structure. The Oort Cloud occupies a region that appears empty, yet it holds trillions of objects. It is sparse, but not void. This challenges how we imagine emptiness. Even the quietest regions of space are full of subtle activity. Now imagine the solar system drifting through the galaxy for billions of years, carrying its planets, carrying its debris, carrying its distant cloud, moving through spiral arms, passing other stars, experiencing gravitational tides. This motion is slow, almost imperceptible, but over time, it reshapes everything. The Oort Cloud stretches, contracts, loses material, gains visitors. It adapts to its environment, just like everything else in the universe. Nothing is static. Even the most distant frozen regions evolve. Now consider humanity's place inside this motion. We live on a planet orbiting a star. That star orbits a galaxy. That galaxy moves through the cosmic web, and surrounding our star is a hidden shell that marks the boundary between solar and galactic influence. We are embedded inside layers of motion. We are never truly still. Even when standing on solid ground, we are traveling through space at enormous speeds, carried by Earth, carried by the Sun, carried by the Milky Way. The Oort Cloud travels with us. It is part of this shared journey. Now think about legacy. Human structures crumble, civilizations rise and fall, languages disappear, technology becomes obsolete, but gravitational structures persist far longer. The Oort Cloud will outlast nations. It will outlast cities. It will outlast species. It will exist long after our entire civilization is forgotten. This puts human history into perspective, not to diminish it, but to contextualize it. We are part of a much longer story, one that began long before us and will continue long after us. Now imagine the distant future again, when the sun has become a white dwarf, when the planets have shifted outward, when the cloud has thinned. What remains will still carry traces of what once existed. Gravitational scars, orbital patterns, chemical remnants. The universe remembers through structure, not through memory, not through records, but through physical imprints. The Oort Cloud is one of those imprints, a fossil of early planetary chaos, a signature of the sun's violent youth. Now return to the present one final time. Right now, the cloud is quiet, stable, frozen, drifting. Most people will never think about it. Most will never hear its name. And yet, it surrounds them. It surrounds every moment of their lives. It wraps around the solar system silently, a distant presence, invisible, persistent, real. The Oort Cloud does not demand attention. It does not announce itself. It simply exists. And sometimes, when a comet appears in the sky, when a bright tail stretches across the darkness, it briefly reminds us that something ancient has arrived from very far away, from the hidden shell around our sun. And then it disappears again, returning our attention to the small world beneath our feet, while the vast structure around us continues to drift quietly, endlessly. In the end, The Oort cloud is not something we will ever touch. It is not something we will ever walk on, not something we will ever colonize, not something that will ever become familiar. And that is precisely what makes it powerful. It represents a frontier that exists not for conquest, but for understanding. Because some regions of the universe are not meant to be reached physically. They are meant to be understood conceptually. The Oort cloud exists at the boundary of human reach, not because it is forbidden, but because it is distant in every possible sense, distant in space, distant in time, distant in accessibility, yet it is still part of our home. This contradiction defines much of astronomy. We belong to structures we cannot see. We are influenced by regions we cannot reach. We are shaped by processes that operate far beyond human lifespans. The Oort cloud embodies all of this. Now imagine standing on Earth again, not as an observer of stars, but as part of a cosmic system. Above you is the atmosphere. Beyond that, space. Beyond the planets, debris fields. Beyond that, a vast invisible shell. And beyond that, the galaxy. You are not isolated. You are nested, layered inside layers, wrapped inside gravity, carried through the universe by forces you cannot feel. This perspective changes what it means to exist. It means that your location is not fixed. You are moving through space even when you feel still. Earth rotates, Earth orbits. The sun travels around the Milky Way, and the Oort cloud moves with it, a silent companion to the solar system's journey. Now consider how fragile this arrangement truly is. A single close stellar encounter could reshape the cloud. A shift in galactic environment could strip it away. The sun's evolution will eventually dissolve it. Nothing is permanent. Even the most distant structures are temporary. They last long enough to feel eternal, but eventually they fade. The Oort cloud is already fading, slowly losing material, slowly thinning, slowly merging back into interstellar space. It is not disappearing dramatically, it is dissolving quietly, just as many cosmic structures do. This quiet fading is one of the most common patterns in the universe. Stars fade. Galaxies fade, energy spreads, complexity declines. Everything moves toward equilibrium. The Oort cloud is part of this process. It is not immune to cosmic aging. Now think about how strange it is that we exist during this particular moment, a time when the sun is stable, when the cloud is intact, when Earth is habitable, when intelligence has emerged. This alignment is temporary. It will not last forever. We are witnessing a rare configuration in cosmic time, one that allows both life and understanding to coexist. This moment will pass, but while it exists, it allows us to look outward, to reconstruct the past, to imagine the future, to understand structures far beyond our physical reach. The Oort cloud is one of those structures, a distant witness to everything that came before us and everything that will come after. Now imagine the universe billions of years from now, long after the sun is gone, long after the Milky Way has merged with Andromeda, long after stars have burned out. There will be no Oort cloud, no planets, no familiar structures, only remnants, particles drifting in expanding space. And yet, the fact that the Oort cloud once existed will still matter, because it shaped what came before, because it influenced planetary evolution, because it contributed to the story of life on at least one world. Cosmic structures do not need to last forever to be important. They only need to shape what follows. Now return to the present for the final time. Right now, the Oort Cloud surrounds you. Not visibly, not dramatically, but physically, gravitationally. It is part of the same system that holds Earth in orbit, part of the same structure that defines the Sun's influence, part of the same cosmic network that connects stars to galaxies. It is there when you sleep, there when you wake, there when you look up at the night sky, even if you never think about it, even if you never see it. It remains silent, frozen, ancient, a hidden shell around our solar system, not demanding attention, not seeking recognition, simply existing. And perhaps that is the most powerful thing about it, that in a universe full of explosions, collisions, and violent events, one of the largest structures connected to our star exists quietly, without light, without sound, without movement that we can see, only through slow gravitational motion, only through deep time, only through subtle influence. The Oort Cloud does not announce itself. It does not shine. It does not burn. It only waits, drifting at the edge of the sun's reach, holding the memory of the solar system's birth, and carrying the quiet truth that even the most distant parts of our cosmic home are connected to us, whether we see them or not, whether we understand them fully or not. They remain part of the same story, the same gravity, the same universe. And that story is still unfolding, silently, endlessly. There is one last thing the Oort Cloud teaches us. Not about astronomy, not about gravity, not about comets or stellar evolution, but about perspective. Because when you truly understand how far the solar system extends, how much of it is invisible, how slowly it changes, and how quietly it interacts with the galaxy, you begin to see your place differently. Right now, you exist on a small rocky world, orbiting a medium-sized star, inside one ordinary galaxy, in a universe filled with billions of others. And yet, surrounding you is a structure that stretches almost halfway to the nearest star, a hidden shell, a gravitational footprint, a reminder that home is larger than we ever imagined. The Oort Cloud is not dramatic. It does not glow. It does not erupt. It does not demand attention. But it is vast, and sometimes the most powerful things in the universe are not the loudest. They are the quietest, the slowest, the oldest. Now imagine this final image: the sun drifting through the Milky Way, carrying its planets, carrying its debris, carrying its distant cloud, moving through spiral arms, passing ancient stars, crossing invisible currents of gravity, everything traveling together, everything bound together, everything shaped by motion. The Oort Cloud moves with the sun. It is not stationary. It is not anchored. It is part of a journey that began billions of years ago and will continue long after the sun itself fades. This means the solar system is not just a place. It is a process, a moving structure, a living gravitational pattern. Now think about time one last time. 4.5 billion years ago, the sun formed. Soon after, the Oort Cloud began to take shape. For billions of years, it has remained, quietly orbiting, slowly evolving, barely changing. Human history occupies less than a fraction of a percent of this timeline. Yet within that tiny slice of time, we developed science. We learned physics. We learned how gravity works. We learned how to trace invisible structures through mathematics. We learned how to detect the unseen. And because of that, We now know that this massive hidden shell exists. This knowledge itself is remarkable. It proves that intelligence can reach beyond physical limits. That understanding does not require direct contact, that the universe can be decoded through observation and reasoning. The Oort Cloud exists at the edge of what we can observe directly, but not at the edge of what we can understand. Now imagine the future again, long after Earth is gone, long after the sun has transformed, long after the Oort Cloud has thinned and scattered. What will remain is not the structure itself, but the influence it once had, the material it delivered, the impacts it triggered, the chemistry it preserved, the role it played in shaping planetary history. The universe does not preserve objects forever. It preserves consequences. Every structure leaves behind traces. Every process reshapes what comes next. The Oort Cloud's greatest legacy will not be its ice or its distance. It will be its effect on the evolution of the solar system. Now return to the present moment. Tonight, this moment, you are surrounded by something ancient, not visibly, not tangibly, but physically, a distant shell of frozen worlds, circling silently, waiting patiently, drifting slowly. You will never feel its gravity directly. You will never see its edge with your eyes, but it is there, above you, below you, in every direction. It is part of your cosmic environment, just as much as the sun, just as much as the moon, just as much as Earth itself. And perhaps that is the most humbling realization, that the universe does not place us at the center, but it does place us inside something vast, inside structures larger than imagination, inside systems older than civilization, inside patterns that will outlast our species. The Oort Cloud is one of those patterns, a quiet reminder that our existence is nested inside layers of cosmic history. Now imagine turning off all the lights on Earth, standing beneath a perfectly dark sky. Looking up, you would see stars, but you would not see the cloud. And yet, it would still be there, invisible, silent, surrounding everything you know. This is how much of the universe exists, not for display, not for spectacle, but simply as structure, as consequence, as the natural result of gravity and time. And in that silence, in that darkness, in that distant frozen shell, there is a strange sense of belonging, because even though the universe is vast and indifferent, it still carries us, it still holds us, it still connects us to places we will never visit, to times we will never see, to structures we will never touch. The Oort Cloud is one of those connections, a hidden bridge between the sun and the galaxy, between formation and dissolution, between what once was and what will one day fade away. And while it remains, quietly drifting at the edge of the sun's reach, it continues to tell the same story, a story of gravity, of motion, of time, of impermanence, of scale, and of our place inside a universe that is far larger, older, and more complex than it appears. This is the hidden shell around our solar system. And this is where the journey ends.